The advent of horizontal well technology has driven logging companies to develop new approaches for measuring multi-phase flow in horizontal wells. Each of the three leading oil field service companies has responded by developing tool strings which integrate measurements from both conventional and newly developed special devices to record flow characteristics in horizontal wells. This presentation will describe the special tool strings developed for this purpose. To determine flow rates of each produced fluid in a wellbore, both the velocity and the volumetric fraction, or holdup, of each phase must be measured. The velocity of a given phase, multiplied by its holdup, and then multiplied by the cross-sectional area of flow, yields the wellbore flow rate of that phase. Temperature and pressure are then factored into the equation to convert downhole flow rates to standard conditions at the surface. Logging tools then must be able to measure the velocity and holdup of each phase along a horizontal wellbore to describe the multi-phase flow characteristics in a horizontal well. Schlumberger's flagship tool string for measuring flow in horizontal wells integrates conventional spinner, temperature, and pressure measurements with measurements from such special devices as the FlowView Plus tool and the Reservoir Saturation Tool, or RST. The flagship tool string employs non-radioactive liquid tracers to determine oil and water velocities, and also uses the oxygen activation process to measure water velocity alone. Gas velocity is not measured. However, Schlumberger is currently developing a tool to address this issue. The tracer method uses special liquids that are designed to mix only with the water phase or with the oil phase of the production stream. The tracers contain gadolinium salts, which produce high gamma ray counts when irradiated. In the horizontal wellbore, the oil tracer and the water tracer are ejected into the production stream by the fluid marker injector, where they mix with their respective phases. The water and oil phases are periodically irradiated as they flow past the RST's neutron generator. As a result of the irradiation, gamma rays are given off by the tracers in each phase and are measured as the tracers flow past the RST gamma ray detectors. Phase velocity is determined by measuring the time required for each tracer to flow the known distance from the ejector to the detector. A second technique for measuring water velocity employs the oxygen activation process. In this process, the Reservoir Saturation Tool emits a neutron pulse, which activates oxygen atoms in the water to produce a radioactive isotope with a half-life of 7.1 seconds. The activated oxygen isotope emits gamma rays within the water phase, which are measured as they flow past 3 gamma ray detectors on the tool. Velocity of the water phase is determined by measuring the time required for the activated oxygen to flow the known distance from one gamma ray detector to the next. The flagship tool string uses another set of special devices, the FlowView Plus sondes, to measure two-phase holdup that is the fraction of either water and oil or water and gas within a wellbore cross-section. 8 resistivity probes, as seen here, spaced at 45-degree intervals, detect the interface between phases. When 3 phases are present, the Reservoir Saturation Tool is used to measure gas holdup. To measure gas holdup, the RST emits a neutron pulse and then analyzes the gamma ray spectrum measured by the near and far gamma ray detectors. The relative amounts of carbon and oxygen in the flowing fluid are analyzed using inelastic gamma ray spectroscopy. The near to far count ratio is particularly sensitive to gas, thus allowing gas holdup to be estimated. Though the flagship is capable of determining gas holdup, it cannot measure gas velocity. Halliburton has developed 2 logging tools to address the challenge of measuring multi-phase flow in horizontal wells. The gas holdup tool and the Spectra Flow Log are designed to work in horizontal, deviated, and vertical wells. Each tool has a modular design that allows other sensors, such as the spinner, caliper, temperature, pressure, and fluid density sondes, to be run on the same logging pass. The gas holdup tool employs a cobalt-57 source and a scintillation detector to determine fluid holdup. When three phases are present, the tool measures gas holdup. In the absence of gas, the tool can differentiate oil from water holdups. The scintillation detector counts gamma rays that are scattered back from the production fluids as they pass the detector. The magnitude of the count rate is directly related to the gas holdup. Halliburton's Spectra Flow Log uses a pulsed neutron generator and two spectral gamma ray detectors to obtain oxygen activation measurements that are used to calculate water phase velocity. It can also be used for distinguishing water flow inside the casing from flow outside the casing. The Spectra Flow Log operates in either the continuous logging mode or the stationary impulse mode. In the continuous logging mode, the pulsed neutron generator is used to activate oxygen in the water. The activated oxygen gives off gamma rays that are measured as the water flows past the first and second spectral gamma ray detectors. As the water phase travels between the two detectors, the gamma ray intensity decreases. This decay level is a function of the half-life of activated oxygen and the time it takes the water to flow the known distance between detectors. The linear velocity is determined from the ratio of count rates between the first and second detector. In the stationary impulse method, the pulsed neutron generator operates as the tool is held stationary. The count rate in each detector is recorded, and then the generator is shut down. When shut down, the count rates will eventually drop to background level. Fluid velocity is calculated as the distance from the source to the detector, divided by the time it takes for the count rate to drop to background levels. This overview has outlined different approaches offered by service companies for characterizing multi-phase flow in horizontal wells. Fluid flow in horizontal, high-angle, and undulating wellbores is difficult to characterize, and some measurement techniques work better in part of the well than they do in other parts. The service companies are developing and testing new tools and measurements to address the shortcomings of current tool strings. By combining the best of conventional and special technologies to measure conditions in your wellbore, you can learn more about the location of fluid entry and, if necessary, plan remedial steps to optimize production in your horizontal well.